Everything around you was born in a stellar event. The oxygen in your next breath, the iron in your blood, even the silicon in the device you are using right now, all share a cosmic origin. This is the story of how the universe built itself from almost nothing into the rich world we know. By the end, you will see the night sky not as distant lights, but as the ancient workshops that constructed your very body. How did we get from a universe of only two simple elements to the complexity of life itself? What kind of cosmic process forges something as precious as gold? The answer lies in the magnificent final chapters of Stars. What does it mean to be made from the material of ancient suns? This initial cosmic forge operated for only a handful of minutes. In that fleeting, searing moment following the Big Bang, the entire universe was a single, unimaginably hot nuclear reactor. Protons and neutrons slammed together, fusing into the very first atomic nuclei. When the universe expanded and cooled enough to stop this frantic process, it left behind a specific and limited legacy. The inventory was starkly simple, a universe composed almost entirely of just two elements. Hydrogen, the simplest and lightest, made up about 75% of all normal matter. Helium accounted for nearly all the rest. Only the barest, most minuscule traces of lithium were forged. Then the cosmic fires went out. For the next several 100 million years, the universe expanded in a profound and elemental silence. There were no new elements being created anywhere. This was the primordial reality, a vast, dark, and simple cosmos. There was no oxygen for water, no silicon for rock, no carbon, the fundamental building block of life as we know it. Every ingredient for planets, for oceans, for living creatures was completely absent. The periodic table, as we understand it, was essentially blank beyond those first three boxes. This presents the central mystery of our material existence. How did we journey from a universe containing only hydrogen and helium to one filled with over 90 naturally occurring elements? The transition required a new kind of cosmic factory, one far more powerful and complex than the brief furnace of the Big Bang. That factory would be the first generation of stars, colossal structures born from that primordial hydrogen and helium gas. Their brilliant lives and dramatic conclusions would irrevocably change the composition of everything. From that silent, elemental darkness, the first giants awoke. These were the population 3 stars, colossal structures born solely from the primordial hydrogen and helium gas that filled the young universe. With no heavier elements to help them cool and fragment, these clouds collapsed into monsters, stars hundreds of times more massive than our own sun. Their scale is almost impossible to comprehend. If one sat in our solar system, its outer edges might swallow the orbit of Saturn. Within their hearts, gravity generated pressures and temperatures so extreme they became cosmic pressure cookers of unprecedented power. Here, nuclear fusion did not just create helium, it became an unstoppable chain reaction. The core became a layered onion, fusing heavier and heavier elements in a desperate race against time. Helium fused into carbon, carbon into oxygen, oxygen into neon and magnesium. For the first time since the Big Bang's first minutes, new atomic nuclei were being forged in the universe. But this furious brilliance demanded a high price. A star that massive burns its fuel not for billions of years, but for a mere few million. They lived with ferocious intensity and faded shockingly young, like cosmic fireworks that vanish in a blinding flash. Yet their dramatic and inevitable transition was not a conclusion. It was the essential delivery mechanism. The passing of these first giants was the universe's only way to send those newly forged elements out of their stellar furnaces and into the wider cosmos, scattering the raw materials for everything to come. This steady, step-by-step construction within a star's core is a cosmic form of alchemy. It begins with the simplest of ingredients, hydrogen, the universe's most abundant raw material. Under the immense pressure and heat generated by a star's own gravity, these hydrogen nuclei are forced together. They overcome their natural repulsion and fuse, creating a new nucleus of helium and releasing a tremendous burst of energy. This is the fundamental reaction that powers stars like our own Sun, a process that can continue stable and steady for billions of years. It is the first and most common element factory in the cosmos, transforming the primordial fuel of the universe into something new. But for a star, helium is not an end product. It is simply a new kind of fuel waiting for the right conditions to ignite. In a star more massive than our Sun, the story does not end there. As the hydrogen in the core is exhausted, gravity begins to win its long battle. The core contracts, growing even hotter and denser. When it reaches a critical temperature of around 100 million degrees, a new chapter begins. The accumulated helium atoms, once a byproduct, now become the primary fuel. They begin to fuse together, 3 helium nuclei combining to form 1 nucleus of carbon. This is a monumental step, the creation of the very atom that is the backbone of all known life. With carbon now present, the stellar forge gains a new tool. The carbon nuclei can fuse with more helium, creating oxygen. In the hottest, most massive stars, this chain reaction continues, building heavier elements in successive shells within the star's heart. It becomes a layered structure like the concentric layers of an onion. At the center, the hottest region fuses carbon into neon and magnesium. Around that, a shell fuses helium into carbon. And in an outer shell, hydrogen still fuses into helium. Each new floor in this elemental skyscraper requires a more intense environment than the last, a higher temperature and pressure to force the increasingly large and positively charged nuclei together. This process, stellar nucleosynthesis, is the universe's primary method for creating all the elements from carbon up to iron. It is a slow, methodical, and ongoing construction project happening inside billions of stars across the galaxy right now. Every atom of oxygen you breathe, every atom of silicon in a grain of sand, every atom of calcium in your bones was forged in this precise, layered environment inside a living star that came before our own Sun. It built the universe's elemental foundation, transforming the simple 2-element cosmos into one rich with the chemical diversity necessary for rocky planets and, ultimately, the chemistry of life. But this magnificent factory has a strict and ultimate limit, a boundary written into the laws of physics that not even the most massive star can cross. Iron marks the ultimate boundary of a star's peaceful existence. Up to this point, every fusion reaction in the stellar core has been a source of power. Fusing hydrogen into helium, helium into carbon, carbon into oxygen, each step releases a burst of energy that radiates outward, creating an immense pressure that pushes back against the relentless inward crush of gravity. This balance between the outward push of fusion and the inward pull of gravity is what allows a star to shine steadily for millions or billions of years. It is a stable, self-regulating system, but iron changes everything. When a star's core finally begins fusing silicon into iron, it crosses a line from which there is no return. The physics behind this is both simple and profound. Fusing elements lighter than iron releases energy. It is an exothermic process, but fusing iron nuclei together does the opposite. It requires an input of energy. It is endothermic. Think of it like trying to keep a campfire burning by adding wet logs. They soak up the heat instead of providing it. Inside the star, iron becomes that wet log. It is nuclear ash. As this iron core grows layer by layer, it is no longer a power plant. It is a dead weight. The star's central engine, after a lifetime of brilliant service, begins to shut down. With the outward pressure from fusion suddenly ceasing, the balance that defined the star's entire life is shattered. Gravity, patient and undefeated, now has nothing left to push against. The consequence is immediate and profound. The star's outer layers, millions of miles of superheated plasma, begin an unstoppable descent toward the silent iron heart. This transformation happens in a matter of seconds. The core itself is compressed by the unimaginable weight descending upon it, becoming so dense that protons and electrons are forced together, merging into neutrons. In this final, pivotal act, the core stiffens into an ultra-dense sphere of neutron matter, a last-ditch barrier against total collapse. But the energy released in this sudden halt is beyond comprehension. The incoming material meets this new, rigid core and rebounds in a titanic shockwave that blasts outward through the still descending star. This is the moment of cosmic transformation. The star does not fade quietly. It erupts in a supernova, a flash of light that can outshine an entire galaxy. It is within this unimaginable forge, in the chaotic seconds of the explosion itself, that the universe finally breaks through the iron limit. The intense flood of neutrons, the extreme temperatures and pressures of the blast, allow for the rapid capture of particles, forging all the elements heavier than iron. The gold in a wedding ring, the silver in a photograph, the uranium deep within the Earth, every one of these heavy nuclei is a relic of a star's final, brilliant second. The supernova is the universe's ultimate crucible, and its explosive transition is the necessary birth cry for the rest of the periodic table. A supernova is the universe's ultimate pressure cooker. In the final moment of a massive star's life, the collapse of its core triggers a rebound of unimaginable force. The energy released in that single event can briefly outshine every star in its host galaxy combined. Within this maelstrom, matter is subjected to conditions so extreme they cannot be replicated anywhere else in the present-day universe. It is a chaotic forge of neutrons, protons, and raw energy, where the final and most precious chapters of the periodic table are written. This is where the story of gold truly begins. The process that creates these heaviest elements is called rapid neutron capture, or the Are process. Picture an atomic nucleus caught in a torrent, a flood of neutrons so dense and sudden that the nucleus cannot stabilize between captures. It absorbs neutron after neutron, bulking up in weight almost instantaneously. These newly formed nuclei are wildly unstable. To find balance, some of those newly added particles undergo a transformation, turning into protons. This shift changes the very identity of the element, climbing the periodic table in great leaps. In the span of mere seconds, nuclei are built up into the heaviest of elements, like uranium, platinum, and gold. Then the supernova does its most crucial work. It scatters the harvest. The titanic shockwave from the rebounding core blasts outward, dispersing the star's material. It flings these newly forged heavy elements, along with all the carbon, oxygen, and iron created during the star's long life, out into the vast spaces between stars. This enriched gas, the interstellar medium, becomes the raw material for the next generation. Every heavy atom in our solar system, from the lead in a pencil to the iodine in our bodies, owes its existence to such an explosive stellar event. The supernova is not merely an end, it is a necessary act of cosmic dispersal, seeding the galaxy with the ingredients for planets, oceans, and life. But the story of gold has a surprising second chapter. For decades, astronomers believed supernovae were the sole source of the universe's heaviest elements. Then, in 2017, a monumental observation rewrote the cosmic recipe book. Scientists detected not just light, but gravitational waves, ripples in spacetime itself, coming from a distant galaxy. The source was the collision of two neutron stars, the ultra-dense cores left behind after those giant stellar explosions. This event, known as a kilonova, revealed itself as a far more prolific and efficient cosmic goldsmith. Imagine the sheer density of a neutron star. A single teaspoon of its material would weigh as much as a mountain. Now picture two of these incredible objects, locked in a final, decaying orbit, destined to merge. When they finally come together, the event unleashes conditions even more extreme than a supernova. A maelstrom of neutrons is ejected, creating the perfect environment for the rapid neutron capture process on a truly colossal scale. In the brilliant flash of the kilonova, more gold, platinum, and other rare earth elements can be forged in seconds than a typical supernova might produce in its entire life cycle. The observation in 2017 provided the definitive evidence, the spectroscopic signature of these heavy elements being created in real time and cast out into the cosmos. It confirmed that the universe operates multiple, spectacular foundries for its most precious materials. The gold in a piece of jewelry likely originated not from one dying star, but from the incredible merger of two. These cosmic events are the ultimate alchemists, sprinkling newly minted treasure across the galaxies. They ensure that future solar systems will have the raw ingredients for complex worlds, weaving these rare elements into the fabric of new beginnings. The universe's elemental symphony is not composed solely of explosive crescendos. For every star that ends its life in a cataclysmic supernova, countless others, like our own sun, face a more serene and gradual transformation. Their final act is not a violent blast, but a gentle, luminous exhale that paints the cosmos with some of its most breathtaking art. This is the story of the Planetary Nebula, a cosmic bloom born from a quiet stellar transition, and the patient, meticulous alchemy that occurs within. When a star similar to our Sun exhausts the hydrogen fuel in its core, its long era of stable fusion comes to an end. The core contracts and heats up, igniting the helium that has accumulated over billions of years. This new energy source causes the star's outer layers to swell dramatically, transforming it into a red giant, a vast, cool, and luminous sphere. In this phase, the star becomes unstable. Its outer envelope, now only loosely bound by gravity, begins to pulse and drift away in a series of gentle but persistent stellar winds. Over thousands of years, these winds peel away the star's atmosphere, layer by layer, exposing its intensely hot core. This core, now a white dwarf star, emits powerful ultraviolet radiation that illuminates the expanding shell of ejected gas, causing it to glow with ethereal colors. What we see from Earth is the Planetary Nebula, a magnificent and often symmetrical cloud of gas and dust, a final luminous signature of a star's long journey. But this serene process is not just a beautiful spectacle, it is a vital and efficient chemical factory. Deep within the red giant's interior before its final shedding, a different kind of element creation takes place. This is the slow neutron capture process, or the S process. Unlike the frantic neutron flood of a supernova or kilonova, the S process is a methodical, patient addition. Neutrons are added to existing atomic nuclei like iron seeds, one at a time. After each capture, the nucleus has time to stabilize, sometimes decaying into a different element before the next neutron arrives. It is a slow, step-by-step climb up the periodic table. This gentle, internal cooking is what produces a specific family of heavier elements, including strontium used in some fireworks, barium, and lead. When the stellar winds finally carry the star's outer layers into space, they carry these newly forged elements with them, a quiet gift to the interstellar medium. So while supernova and neutron star mergers create the universe's gold and uranium, the peaceful passing of sun-like stars is responsible for seeding the galaxy with other crucial heavy elements. This gentle expulsion ensures that the cosmic inventory is rich and varied. The next time you see an image of a glowing planetary nebula, remember you are not just looking at a beautiful cosmic ghost. You are witnessing a star's final, generous contribution, a slow and steady breath that scatters the chemical seeds for future solar systems and perhaps for worlds like our own. This enriched gas and dust becomes the raw material for the universe's next great act of creation. After a supernova's brilliant flash fades or a planetary nebula's glow dims, the newly forged elements do not simply drift forever in the void. They become part of vast, cold clouds that drift through the spiral arms of galaxies, cosmic recycling centers known as molecular clouds. These are the stellar nurseries. Within their dark, dusty folds, the legacy of ancient stars is patiently gathered. Gravity, the universe's great architect, begins its slow work, pulling pockets of this enriched material together. As a cloud fragment collapses, it spins and flattens into a swirling disk of gas and dust around a growing protostar at its center. This is the birth of a new solar system, but it is a birth with a profound inheritance. The star that ignites at the heart of this system is no longer a pure, primordial giant like the first stars. It is a star of the second or third or thousandth generation. Its composition includes not just hydrogen and helium, but also traces of all that came before, the carbon, oxygen, iron, and even gold sprinkled into the mix by its stellar ancestors. The protoplanetary disk around this young star is where the stardust truly finds its purpose. Microscopic grains of silicate rock and ices, each speck containing atoms forged in different stars at different times, begin to stick together. They form pebbles, then rocks, then planetesimals, the building blocks of worlds. In the warmer inner disk, where volatile ices cannot survive, these collisions build rocky, metallic planets like Earth. Farther out, where it is cold enough for ices to exist, the process creates the massive cores that go on to become gas giants. Every asteroid, every comet, every planet is an assembly of this cosmic heritage. Our own solar system is a perfect example of this magnificent recycling process. It formed from such an enriched cloud roughly 4.6 billion years ago. The sun ignited, and in the disk that surrounded it, the material of countless ancient stellar lives coalesced. The iron that pooled at Earth's core came from the final moments of a massive star. The silicon in our continents was forged in the layered heart of a red giant. The carbon that forms the basis of every molecule in our bodies was created in the furnace of a star that shone billions of years before our sun was even a glimmer in a nebula. You are not just living in the universe, you are a temporary collection of its most ancient and well-traveled materials. Every atom in your hand, in the air you breathe, in the ground beneath your feet, carries the history of a stellar journey that began long ago, a gift from the cosmos that allows you to be here today. Of all the elements forged in stars, carbon holds a unique and special place. It is the universal connector, the element with a special ability to link hands with itself and with others, forming long chains, intricate rings, and vast molecular architectures. This versatility makes it the absolute foundation of biochemistry, the essential ingredient for every living thing we know. Yet the cosmic story of how carbon came to be is one of astonishingly precise good fortune. Its creation hinges on a stellar process so finely tuned that it feels almost like a cosmic invitation. This process is called the triple alpha process, and it occurs in the hearts of red giant stars. Alpha particles are essentially helium nuclei, and the process requires 3 of them to come together in a specific sequence to build a single carbon nucleus. The first step is relatively straightforward. 2 helium nuclei fuse to form an unstable, fleeting version of beryllium. The challenge is the third step. That beryllium nucleus exists for only a vanishingly short instant before it falls apart. For carbon to form, a third helium nucleus must strike this temporary beryllium target at exactly the right moment. It is a cosmic game of chance played out under immense heat and pressure. What makes this possible is a remarkable bit of nuclear physics known as resonance. Think of it like pushing a child on a swing. If you push at just the right moment in the swing's arc, with just the right amount of force, you add energy efficiently and the swing goes higher. Push at the wrong time and your effort is wasted. Inside a red giant, the energy states of the beryllium nucleus and the incoming helium nucleus align in a perfect resonant harmony. This resonance dramatically increases the probability of that crucial third collision happening before the beryllium disintegrates. Without this specific, finely tuned resonance, the triple alpha process would be hopelessly inefficient. Stars would struggle to produce carbon at all, sprinkling only trace amounts into the galaxy instead of the abundant supply we find. This precise nuclear arrangement is why scientists sometimes speak of the carbon miracle. The fundamental constants of our universe, the strengths of the forces that bind nuclei together, appear to be set within a very narrow range that allows this resonance to exist. A slight adjustment to these constants, and the music of nuclear forces would play a different tune, one where carbon might be a cosmic rarity. The fact that it is not, that stars are prolific carbon factories, is a profound reason our universe is chemically rich enough for life to emerge. Every complex molecule in your body relies on this stellar good fortune. The carbon atoms in the glucose that fuels your cells, in the strands of DNA that encode your being, in the very paper of a book or the graphite in a pencil, all share this origin. They were assembled inside a red giant star billions of years ago, through a process of resonant chance, and then gently expelled into the galaxy to await their next role. We are not just stardust, we are carbon-based stardust, the product of a universe whose physical laws conspired to make our existence chemically possible. Yet for all the vital importance of carbon, it is not the most abundant legacy of stellar furnaces in our everyday world. That title belongs to oxygen. It is the third most common element in the entire cosmos, the O in H2O, and the very reason our blood can carry energy to our cells. Like carbon, its origin story is written in the hearts of massive stars, but its journey into the universe required a far more dramatic exit. Oxygen is forged during a star's later, more active chapters. After a star has built a core of carbon through the triple alpha process, the stellar furnace intensifies. As the core contracts further under gravity's steady pressure, temperatures soar past 600 million degrees. At this threshold, a new fusion reaction ignites. Carbon nuclei begin to collide and fuse with helium nuclei. This marriage of elements, a process called alpha capture, creates new atomic nuclei of oxygen. It is a prolific production line. For stars more than 8 times the mass of our Sun, this oxygen forging occurs on an immense scale, creating vast reservoirs deep within the star's layered interior. But there is a critical catch. This oxygen, so essential for future worlds, is secured within. It is held under immense layers of stellar material, contained in the star's dense core and surrounding shells. For it to ever become part of a planet, an ocean, or a lung, it must be set free. The gentle stellar winds of a sun-like star are not powerful enough to release these deep, heavy elements. The only process capable of such a task is the tremendous transformation of a supernova. When that massive star reaches its iron limit and undergoes its great change, the rebounding wave does more than create other elements. It acts as the ultimate cosmic courier, expanding outward with incredible force. In that magnificent instant, the star's layered interior is unveiled. All the oxygen forged over millions of years, along with silicon, magnesium, and sulfur, is carried into interstellar space. The supernova disperses these raw materials like a gardener casting seeds to the wind. The abundance of oxygen in a galaxy, therefore, becomes a living record. It is a direct signature of the many massive stars that have completed their cycles there. A galaxy rich in oxygen is one that has witnessed generations of these stellar giants concluding their lives in spectacular fashion. So the air you are breathing right now is not simply empty space. It is filled with atoms that were once at the heart of a distant, colossal sun. Every molecule of oxygen that sustains you participated in one of the universe's most energetic events, a final brilliant farewell that shared these essential atoms with the future, including with you. Silicon is the universe's master mason, the architect of solid ground. While oxygen fills our lungs and carbon builds our bodies, silicon is what gives a planet its bones. This element, so common in the rocks of Earth and the sands of distant worlds, has a dramatic and precise origin story. It is forged not in the gentle winds of a fading sun, but in the frantic, final hours of a true stellar giant during a brief and intense chapter known as silicon burning. This process is the last act of peaceful fusion a star will ever know. Deep within a massive star, after its core has fused hydrogen to helium, helium to carbon, and carbon to oxygen, the temperature soars past 3 billion degrees. At this unimaginable heat, the oxygen nuclei themselves begin to collide and fuse. The primary product of this furious reaction is silicon. For a matter of days, the star's innermost heart becomes a silicon factory, a place where the raw material for future continents is assembled atom by atom. But the process does not stop there. In that same searing environment, silicon nuclei can then fuse with helium nuclei, climbing the periodic table one step at a time to create sulfur, argon, calcium, and others, in a steady march toward the final element, iron. This layered fusion, happening in mere days, builds up the star's central core into a dense, onion-like structure of increasingly heavy elements, with silicon as a crucial, abundant layer. Then the star reaches its inevitable limit. When silicon begins fusing into iron, the power plant shuts down, the core collapses, and the supernova explosion ensues. This tremendous event is the crucial delivery mechanism. All that silicon, painstakingly created in the star's final days, is now cast into the surrounding space. It is flung outward in a cloud of gas and dust, enriched with this new, stony ingredient. In the cold quiet that follows, this silicon finds its purpose. As new solar systems condense from such enriched clouds, the silicon atoms readily link with oxygen atoms to form molecules called silicates. These silicate minerals are the clay of the cosmos. They are the first solid particles to condense as a protoplanetary disk cools. Tiny grains of silicate dust stick together, forming pebbles, then rocks, then mountain-sized planetesimals. Through countless collisions and accumulations, these become the cores of rocky worlds. So the ground you stand on is not just ancient, it is the product of a specific stellar finale. The silicon in every stone, in every grain of beach sand, in the very bedrock of our continents, was once part of a massive star's final, furious effort to shine. It was cast into the void in a brilliant flash, only to slowly coalesce over billions of years into the solid foundation of our world. Your connection to the cosmos is not abstract, it is literally underfoot, a lasting monument to a star whose transformation allowed Earth to be built. Iron and nickel represent the final stable form of stellar architecture, within the layered heart of a massive star as silicon burning concludes. These are the last elements forged through fusion. Iron, as we know, is the nuclear ash that halts the stellar engine, but its close companion nickel-56 is also produced in abundance during those final frantic moments of core fusion. This isotope is unstable, however, and quickly decays into stable iron. So the legacy of a star's final act is a core increasingly dominated by these two heavy stable metals. They are the end of the line, the point where a star's brilliant internal construction project must cease. Their very stability, which makes them useless as stellar fuel, is what makes them perfect for an entirely different cosmic purpose. When the core collapses and the supernova scatters the star's material, this iron and nickel is flung into the galaxy not as waste but as treasure. In the swirling disk of a new solar system, these dense metals have a natural tendency to sink toward the center of the forming clumps of matter. They are the heavy anchors around which rocky worlds assemble. Our own Earth is a profound example of this inheritance. Deep beneath the mantle and the outer core of liquid iron lies our planet's solid heart, a sphere roughly the size of the Moon. This inner core is composed overwhelmingly of iron and nickel, a metallic heirloom from a star that completed its cycle before our Sun was born. But this ancient stellar material is not merely a dormant relic. It is profoundly active. The difference in temperature between the solid inner core and the liquid outer core, combined with our planet's rotation, drives a massive dynamo effect. This churning of molten iron and nickel generates Earth's magnetic field, an invisible shield that extends far out into space. This magnetosphere is our planet's first line of defense. It deflects the constant stream of charged particles from the sun, the solar wind, that would otherwise slowly strip away our atmosphere. Without this protective bubble, our air and oceans could have been eroded away over billions of years, leaving a barren, exposed rock. So the iron that signaled the end for one star became the protective heart for a living world. The very element that forces a stellar transformation becomes the guardian of a planetary one. We are shielded and thus able to breathe by the enduring core of a long-vanished sun. While iron and nickel form the stable heart of planets, one of the lightest elements presents a cosmic riddle. Lithium, the third element on the periodic table, is an anomaly. Its story defies the simple narrative of creation, revealing a universe where elements are not just forged, but also lost, remade, and meticulously balanced. The journey of a lithium atom is a precarious one, a delicate dance between birth and transformation that challenges our understanding of cosmic history. A tiny amount of lithium was indeed forged in the Big Bang, a relic from the universe's first 3 minutes. Yet when astronomers look out into the oldest stars in our galaxy, the ones that should preserve that primordial signature like a cosmic time capsule, the numbers often do not match. The predicted amount of lithium from the Big Bang and the amount actually observed in these ancient stars can differ by a factor of 2 or 3. This is the lithium problem, a quiet but persistent mystery that suggests our picture of the early universe is still incomplete. The challenge is that lithium is a fragile element. While massive stars build heavier nuclei, the interiors of smaller, sun-like stars act as lithium destroyers. As fresh hydrogen from a star's outer layers cycles down into its hot interior, the intense heat breaks apart the delicate lithium nuclei. A star like our own sun consumes its lithium over its lifetime. So the very act of observing an ancient star to measure primordial lithium is complicated by the star's own internal chemistry, which may have altered its original supply. This means the lithium we see today is not simply a pristine fossil. It is a product that has been changed by billions of years of stellar processing. Yet lithium is also being created anew even now. One of the most fascinating production methods occurs not in the hearts of stars, but in the dynamic spaces between them. This process is called cosmic ray spallation. Imagine a high-energy proton, a piece of an atomic nucleus accelerated to nearly the speed of light by a distant supernova shockwave racing across the galaxy. It collides with a heavier nucleus, perhaps an atom of carbon or oxygen drifting in interstellar space. The impact is so powerful it fragments the larger nucleus, and among those fragments can be new lithium atoms. It is a form of cosmic alchemy through transformation, where one process leads to another. Understanding this full life cycle, from Big Bang birth to stellar processing to interstellar renewal, is crucial for astronomers. Lithium acts as a sensitive diagnostic tool. By measuring its abundance in stars of different ages and compositions, scientists can test and refine their models of both the Big Bang's first moments and the complex internal workings of stellar evolution. Its delicate balance teaches a profound lesson. The history of the elements is not a linear story of accumulation. It is a dynamic cycle of creation, change, and transformation, a narrative where some chapters, like the exact story of that primordial lithium, are still being written in the light of distant stars. The delicate balance of lithium reveals a universe of constant change, where elements are not simply forged and forgotten. This dynamic narrative becomes even clearer when we look at the heaviest members of the periodic table. Their creation is not governed by a single rule, but by two distinct cosmic pathways, each with its own rhythm and setting. These are the slow process and the rapid process, and they are responsible for the entire upper half of the periodic table. The slow process is the universe's patient craftsman. It occurs in the relatively serene interiors of red giant stars, those swollen, aging suns. Here, neutrons are produced in a steady trickle, perhaps one every few days or weeks. A nucleus captures a neutron. Because the supply is so gradual, this new, slightly heavier nucleus often has time to stabilize. Sometimes, through a transformation called beta decay, one of its neutrons will change into a proton. This shifts its identity, moving it one step up the periodic table. Then, after this change is complete, another slow-arriving neutron is captured, and the cycle repeats. It is a methodical, step-by-step climb, like a mason carefully placing one brick at a time. This gentle, internal alchemy is responsible for creating a specific family of heavy elements, including strontium, barium, and a significant portion of the lead found in the cosmos. It is a testament to the quiet, persistent creativity of a star's long journey. In stark contrast, the rapid process is the universe's explosive artist. It requires an environment of unimaginable neutron density, found only in the most catastrophic cosmic events. Here, there is no trickle, only a flood. A nucleus is bombarded by a blizzard of neutrons, absorbing them in rapid succession before it has any chance to stabilize. It grows to an extremely heavy, wildly unstable form almost instantaneously. Only after the neutron storm subsides does this nucleus begin to calm itself, undergoing a rapid series of transformations to change its excess neutrons into protons. This frantic sequence can leapfrog up the periodic table, creating the very heaviest and rarest elements in a single, breathtaking event. This process is the sole cosmic source for gold, platinum, uranium, and other precious, dense metals. It is a forge of sudden, magnificent intensity. Comparing these two methods is like understanding the difference between pottery and stained glass. The slow process is the potter's wheel, where material is shaped gradually, with time for adjustment between steps. The rapid process is the glassmaker's furnace, where raw elements are subjected to a sudden, blinding heat, transforming them in an instant into something brilliant and new. Both methods are essential. The steady work of red giants seeds the galaxy with a foundational layer of heavy elements. The brilliant conclusions of stellar giants then sprinkle in the rarest jewels. Together, these two roads from the hearts of stars ensure that the cosmic inventory is rich with a diversity of atoms, each with its own unique story of creation, written in the speed of a neutron's arrival. The light from a star is far more than just a distant point of brightness. It is a detailed cosmic message, a story encoded in every color and wavelength. To read this story, astronomers rely on a powerful technique called spectroscopy. It is how we transform that faint, twinkling light into a chemical biography of the universe. Every element in the periodic table leaves a unique signature in light, a kind of atomic fingerprint. When starlight passes through a prism or a specialized grating, it fans out into a full spectrum, a rainbow of colors. Embedded within that rainbow are dark lines like barcodes on a product. Each of those lines corresponds to a specific element absorbing light at a precise wavelength. By reading these spectral lines, scientists can determine not only which elements are present in a star's atmosphere or a distant nebula, but also in what quantities. This is how we know the Sun is made mostly of hydrogen and helium. It is how we detected the signature of gold in the aftermath of that neutron star collision. Spectroscopy is our universal translator for the language of starlight. This tool allows us to do something remarkable, to read the history of our galaxy in the chemical makeup of its stars. Think of the Milky Way as a vast library, and each star is a book written in the language of spectral lines. A very old star, one of the first generation to form after the Big Bang, will have a simple chemical fingerprint. Its spectrum shows almost pure hydrogen and helium with only the faintest traces of anything heavier. It is a pristine record of the early universe. A younger star, like our own Sun, tells a more complex story. Its light reveals significant amounts of carbon, oxygen, silicon, and iron. This richer fingerprint tells us the Sun is a descendant, born from a cloud that was already enriched by many generations of earlier stars. We can even find stars with unusual chemical stories. A star showing an overabundance of elements from the rapid neutron capture process, like europium or gold, might be a living witness to a nearby supernova or neutron star merger that occurred just before its birth. By surveying stars of different ages and locations, astronomers can piece together a timeline of elemental enrichment, watching how the galaxy's chemistry evolved from simple to complex over billions of years. This turns the abstract concept of stellar factories into observable, measurable science. We are not just theorizing about processes inside stars, we are collecting the direct evidence they left behind. The light reaching our telescopes today carries the chemical imprint of events that happened long before our planet existed. Every spectrum is a snapshot of cosmic history, allowing us to trace our own elemental origins back to specific types of stellar events. The next time you look up at the stars, remember you are not just seeing points of light. You are looking at countless chemical fingerprints, each one a chapter in the grand story of how a universe of hydrogen became a universe capable of wonder. This stellar recycling system has one final spectacular delivery method. Not all supernovae are born from the collapse of a single massive star. There exists another class, a cosmic detonation so precise and predictable it has become a fundamental tool for measuring the universe itself. These are Type 1, a supernova, and their story begins not with a giant but with a stellar ghost in a binary dance. A white dwarf is the incredibly dense Earth-sized core left behind after a sun-like star sheds its outer layers. It is essentially a sphere of carbon and oxygen, no longer fusing, slowly cooling over eons. But if this white dwarf has a companion star, a living partner orbiting close by, its story can take a dramatic turn. Through complex gravitational interactions, the white dwarf can begin to siphon hydrogen-rich material from its neighbor. This gathered gas accumulates on the white dwarf surface, building up layer by layer over thousands of years. The white dwarf, already under immense pressure from its own gravity, is patiently collecting fuel it was never meant to have. This sets the stage for a transformation of remarkable uniformity. As the gathered mass increases, so does the pressure and temperature at the white dwarf base. There is a critical threshold known as the Chandrasekhar limit. When the white dwarf mass approaches about 1.4 times that of our Sun, the conditions become too extreme for its carbon-oxygen heart to remain stable. In a runaway chain reaction that begins in a fraction of a second, the entire white dwarf undergoes complete thermonuclear fusion. It is not a collapse followed by an explosion, but a total, instantaneous detonation. The star does not leave behind a neutron star or a black hole. It is completely transformed, its entire being converted into energy and newly forged elements in a flash of light that can outshine a galaxy. This specific repeatable process makes Type 1 a supernova cosmic lighthouses, because the explosion always happens at roughly the same mass. The peak brightness is incredibly consistent. Astronomers call them standard candles. By observing how bright such a supernova appears from Earth, they can calculate its true distance with great accuracy. This is how we measure the vast scales of the universe and discovered its accelerating expansion. But beyond their role as measuring sticks, these binary explosions are prolific chemical forges. The intense complete transformation of the white dwarf produces a specific family of elements known as the iron peak. This includes stable iron, nickel, and cobalt. While core collapse supernova from massive stars also create these elements, Type 1 events are a major complementary source, ensuring these crucial metals are abundantly scattered throughout galaxies. This reveals a beautiful duality in cosmic alchemy. The iron in your blood may have come from the dramatic collapse of a massive star core, or it might have been forged in the brilliant final flash of a white dwarf that spent eons quietly gathering material from a companion. The universe does not rely on a single recipe. It employs multiple pathways from solitary giants to binary partners to ensure the galaxy is richly and diversely seeded with the atoms of possibility. The galaxy itself has a chemical history, one that can be read like the rings of a tree. Those spectral fingerprints we collect from stars of different ages reveal a universe that is not static, but one that has been growing richer in atomic diversity over billions of years. This grand, gradual accumulation is known as galactic chemical evolution, and it is the story of how the periodic table itself was assembled, element by element, across cosmic time. In the earliest chapters, the first galaxies were chemically simple places. They were vast clouds of pristine hydrogen and helium, the raw materials left over from the Big Bang. When the first generation of colossal stars ignited within them, their light was the only complex thing about them. These pioneers lived fast and concluded their lives in spectacular supernova, and in doing so, they performed the universe's first act of cosmic alchemy. They scattered their newly forged carbon, oxygen, and traces of heavier metals into the surrounding gas. This was a pivotal moment. The interstellar medium, the reservoir from which new stars form, was no longer pure. It was now slightly enriched. The next generation of stars that condensed from this cloud therefore began their lives with a tiny but crucial inheritance. They were born with a small fraction of heavier elements already mixed into their fuel. When these stars, in turn, reached the ends of their lives, they added their own unique chemical contributions to the mix. A massive star might contribute extra silicon and sulfur. The gentle transition of a sun-like star would sprinkle in strontium and lead. A rare neutron star merger would inject a burst of gold and platinum. With each stellar generation, the galactic reservoir became more chemically diverse, more complex. It was a slow, cumulative process of cosmic enrichment. We can see this history written in the stars themselves. The oldest stars we can find in the Milky Way's halo, relics from nearly 13 billion years ago, have extremely low metallicities. Their light shows barely a trace of any element heavier than helium. They are the living fossils of that early, simple universe. Compare that to a star like our Sun, which is about 4.6 billion years old. Its spectrum reveals a much richer palette of elements, clear evidence that it formed from gas that had been cycled through many generations of stars before it. We are quite literally the products of a galaxy that has spent eons building up its elemental wealth. This gradual enrichment was the essential precondition for everything that followed. A galaxy of only hydrogen and helium can only form giant balls of gas. It takes heavier elements to form dust grains, the seeds of rocky planets. It takes carbon, oxygen, and nitrogen to form the complex molecules that become the basis of chemistry and biology. The fact that we exist on a rocky world surrounded by water and a breathable atmosphere is a direct consequence of this long, patient process of galactic chemical evolution. Our solar system did not form from primordial gas, but from well-recycled material, the accumulated legacy of countless stellar lives that came before. We are not just stardust, we are the refined product of an entire galaxy's historical effort. That scientific fact transforms our understanding of what it means to be human. The calcium that gives your bones their strength was forged in the final, furious burning of a massive star. The phosphorus that forms the backbone of your DNA, the very code of life, was likely created in that same stellar environment or in the explosive aftermath. The iron coursing through your veins, carrying oxygen to every cell, is a direct inheritance from a stellar core that reached its ultimate limit. Trace any element in your body back far enough, and you will find its origin in a cosmic event that predates our solar system. You are not just living in the universe, you are a temporary assembly of its most ancient and well-traveled materials. This connection is more than a list of ingredients. It is a narrative of cosmic recycling written into your very cells. Every breath you take pulls in oxygen atoms that were once part of a red giant star. Every movement you make relies on calcium and iron that were scattered across light years by a supernova's immense energy. The carbon that forms the foundation of every organic molecule in your body was created through that precise, resonant good fortune inside a star billions of years ago. We are the universe's way of gathering its own scattered history into a form that can look back and wonder. This perspective redefines our place in the cosmos. We are not separate observers looking out at a distant foreign sky. We are the cosmos itself become conscious. The stars are not simply distant points of light, they are our long-lost ancestral homes. Their brilliant lives and dramatic conclusions were not random events, but necessary steps in a grand, patient process that made planets and biology possible. When you feel the solid ground beneath your feet or the beat of your own heart, you are interacting with the legacy of stars. This realization bridges the vast scales of space and time, linking the intimate reality of our biological existence directly to the majestic life cycles of celestial giants. We are living proof that the universe possesses not only the ability to create complex matter, but to weave that matter into stories that can, eventually, tell themselves. The cosmic forge never sleeps. Even as you listen, new stars are igniting within stellar nurseries, their light a testament to the enriched gas clouds that birthed them. Across the spiral arms of our galaxy, massive stars are concluding their brilliant lives in spectacular events, scattering another wave of freshly minted elements into the void. The process that built our solar system is not a historical event, it is an ongoing, dynamic feature of the universe. This leads to a profound question about the far future, on scales of time that stretch beyond comprehension. What comes next for the production of elements in a cosmos that is slowly, inevitably changing? The story of cosmic chemistry is entering a new, quieter chapter. Billions of years from now, the great era of widespread star formation will begin to wind down. Galaxies will have consumed much of their free hydrogen gas, the essential fuel for new suns. The brilliant, short-lived massive stars that served as the universe's primary heavy element factories will become increasingly rare. In this future cosmos, the primary sources for new heavy elements will shift from the births and conclusions of giant stars to the mergers of their ancient, dense remnants. The quiet dance of paired systems will become the dominant alchemy. Neutron star mergers, those spectacular kilinovae, will become the primary goldsmiths of the universe. White dwarf interactions and the delicate accretion events that trigger certain supernova will continue to produce iron and nickel. these events are more sporadic, more isolated than the constant stellar events of a young galaxy, but they are no less potent. Each merger is a concentrated burst of creation, injecting a rich dose of rare elements into an interstellar medium that is already complex. Over eons, this slow, punctuated enrichment will continue. The cosmos will gradually grow more metal-rich, meaning the overall abundance of elements heavier than helium will keep increasing, albeit at a much slower pace than in its vibrant youth. The timescales involved here are almost impossible to grasp. We are speaking of hundreds of billions, even trillions of years. Human history, the entire lifespan of our sun, is but a fleeting instant in this grand narrative. Yet, this patient accumulation has a consequence for any worlds that might form in that distant future. A planet condensing from the galactic raw material 10 billion years from now would be born from a more chemically diverse mix than Earth was. It might have a slightly higher natural abundance of precious metals like gold or platinum woven into its very crust from the outset. Its geology and chemistry could be subtly different, shaped by a richer elemental inheritance. This ongoing process means the universe is still writing its material story. The atoms being forged today in a stellar event in another spiral arm will one day drift, cool, and perhaps become part of a new solar system in a galaxy far away. We are living in a cosmos that is not finished creating the ingredients for future possibilities. The legacy of the stars is not static, it is a living, evolving tapestry, and every spectacular stellar conclusion adds another thread to its design. Even with this grand cosmic story mapped out, our picture of stellar alchemy is not yet complete. The universe holds onto some of its most detailed recipes with remarkable secrecy. While we understand the broad strokes of how elements are forged, the precise locations, the exact yields, and the subtle variations in these processes present ongoing puzzles for astronomers. Why, for instance, do we observe stars with surprisingly high amounts of silver or other specific rare Earth elements? The theoretical models of the rapid neutron capture process can produce these metals, but matching the predicted amounts to what we actually see scattered across the galaxy requires incredibly fine-tuning. The conditions inside a supernova or during a neutron-star merger are so extreme and chaotic that computer simulations struggle to capture every nuance. A slight change in temperature, density, or the initial composition can dramatically alter the final elemental output. It is like trying to reconstruct the exact recipe for a complex dish by only tasting it once. You know the main ingredients, but the precise proportions and the order of steps remain elusive. Unraveling these mysteries demands a powerful combination of tools. On one hand, astrophysicists run increasingly sophisticated supercomputer simulations, attempting to model the dynamic physics of these cosmic events in digital laboratories. On the other, astronomers point telescopes at the sky, waiting to catch the next stellar transformation in the act. Every new observation of a distant supernova, or more importantly, a kilonova from colliding neutron stars, is a precious data point. The light from such an event carries the direct spectral signature of the elements being created and flung into space in real time. Each new detection is like finding a missing page from the universe's cookbook, allowing scientists to compare their simulations against reality and refine their models. This iterative process of prediction and observation is how science slowly closes in on a complete understanding. A single kilonova observed in 2017 provided more concrete data on the formation of heavy elements than decades of theory alone. Future events detected by next-generation observatories will help us understand not just if these events create gold, but exactly how much and under what specific conditions. The quest to map every pathway on the periodic table back to its stellar origin is a grand detective story, one where the clues are written in the fading light of the most powerful explosions since the beginning of time. This delicate chain of creation leads to a staggering implication. The specific mix of elements we find in our world, the very chemistry that allows planets and life to exist, hinges on a series of cosmic coincidences so precise they border on the miraculous. If the fundamental rules of our universe were written just slightly differently, the entire story of the elements would collapse. This observation brings us to a deep and reflective concept known as the Anthropic Principle. In its simplest form, it suggests that the universe we observe must be compatible with the existence of observers, because here we are, observing it. It is not a claim of purpose or design, but rather a recognition of a series of astonishingly fortunate breaks in the cosmic narrative. Consider the nuclear forces that govern how particles stick together inside an atom's heart. These forces have very specific strengths, values that were set in the earliest moments of the Big Bang and have remained constant ever since. If the strong nuclear force, the glue that binds atomic nuclei, were just a few % stronger or weaker, the consequences would be transformative for chemistry as we know it. A stronger force might bind protons and neutrons so tightly that hydrogen, the universe's primary fuel, would not exist in its stable form. Stars might never ignite. A weaker force might mean no elements heavier than hydrogen could form at all, leaving a universe forever simple and sterile. The most famous example of this fine-tuning is the carbon resonance we discussed earlier. For carbon to be produced abundantly inside stars, the energy states of the beryllium and helium nuclei must align in a perfect resonant harmony. This resonance is a direct result of the precise values of the fundamental constants. Tweak those constants even a little and the resonance vanishes. The triple alpha process becomes wildly inefficient. Carbon becomes a cosmic rarity, and without carbon, the chemistry of life becomes an impossibility. The universe would still have stars and planets, but they would be built from a different, likely far simpler, set of ingredients. Even the role of iron as the final product of stellar fusion is not an arbitrary stopping point. It is a direct consequence of nuclear physics. The fact that fusing elements lighter than iron releases energy, while fusing iron itself consumes energy, is a fundamental property of matter. If this tipping point were located at a different element, say silicon or nickel, the entire life cycle of stars would change. The brilliant conclusions of these stars might occur earlier or later, with different explosive yields, scattering a completely different elemental palette into space. The planets that formed might have cores of unfamiliar materials, with geologies and chemistries we can scarcely imagine. So, what are we to make of this apparent cosmic fine-tuning? One perspective is that we are simply the beneficiaries of an incredibly long and unlikely lottery. In a vast, perhaps infinite multiverse, countless universes may exist with different physical constants. In most of them, the numbers do not line up, and stars either fail to ignite or burn out without creating the necessary complexity. No planets form, no chemistry evolves, no one is there to notice. We find ourselves in one of the rare, perhaps exceedingly rare, universes where the numbers did allow for carbon-based observers to arise. Our very existence as creatures who can ask these questions selects for this kind of universe. Another perspective is that we are still early in our understanding, and that a deeper, more fundamental theory of physics will one day show why these constants must have the values they do, that they are not random but inevitable. Regardless of the interpretation, the Anthropic Principle serves as a powerful reminder of our profound connection to the cosmos. It underscores that our existence is not a separate event, but the endpoint of a long, delicate, and precisely calibrated chain of events that began with the first fundamental forces and unfolded through the brilliant lives and conclusions of stars. We are not just made of stardust, we are the result of a universe whose basic rules allowed stardust to eventually become conscious of itself. To peer into the heart of a stellar explosion, we must build a star inside a machine. The physics of a supernova or neutron star merger is so overwhelmingly complex that no single equation can describe it. Instead, scientists turn to some of the most powerful supercomputers on Earth, constructing breathtakingly detailed digital models that attempt to recreate, in essence, the final chapter of a star's story. These are not simple animations, they are full-scale virtual laboratories, governed by the fundamental laws of physics as we understand them. Within these simulated worlds, gravity compresses digital matter, nuclear reactions ignite and spread, and shockwaves ripple through a star's layers, all unfolding over mere seconds of simulated time that can take months of real-world computation to complete. The challenge is staggering. A useful simulation must account for a dizzying array of forces and particles all interacting at once. It begins with Einstein's theory of general relativity, which dictates how space and time warp under extreme gravity, especially crucial for modeling the collapse of a stellar core or the spiraling dance of neutron stars. Then comes nuclear physics, with libraries containing data on thousands of possible reactions between different atomic nuclei. The simulation must track how these nuclei form, break apart, and transform as temperatures soar past billions of degrees. Perhaps most elusive are neutrinos, ghostly particles that barely interact with matter. In the incredible density of a collapsing stellar core, these neutrinos become trapped, and their pressure plays a critical role in helping to drive the rebounding shockwave outward. The simulation must model their creation and diffusion. Finally, there is magnetohydrodynamics, which describes how electrically conducting fluids like stellar plasma behave in the presence of magnetic fields. These fields can be twisted and amplified to incredible strengths during a collapse, potentially jetting material out at near light speed. By running these monumental simulations, astrophysicists perform experiments that are impossible in any earthly lab. They can adjust a single variable, like the initial rotation rate of the star or the strength of its magnetic field, and watch how the entire explosive event unfolds differently. They can follow individual tracer particles, watching as a virtual atom of silicon is forged in the final moments of fusion, then caught in the supernova blast, and perhaps transformed into iron or even heavier elements via rapid neutron capture as the shockwave passes. This allows them to make specific predictions, a virtual fingerprint of elemental abundances. They can then compare that predicted fingerprint to the actual chemical signatures astronomers detect in the aftermath of real cosmic events or in the atmospheres of ancient stars. It is a continuous cycle of prediction and observation, where the digital universe helps us interpret the real one. This virtual experimentation reveals details no telescope could ever see. We cannot place a probe inside a star as it undergoes this transformation, but a simulation can freeze time, letting scientists examine the exact conditions in the core just milliseconds before the shockwave forms. They can visualize how turbulent instabilities, like rising plumes of hot matter, help the explosion along. They can witness the formation of a neutron star or a black hole in their digital realm, studying the gravitational waves it should produce. Each simulation is a story of discovery, a test of our deepest understanding of how the universe operates under the most extreme conditions imaginable. When the digital results finally align with the faint light we collect from across the cosmos, it is a moment of profound confirmation, a sign that we are beginning to truly comprehend the magnificent cosmic alchemy that built our world. The ultimate prize in this cosmic detective story is a flash of light from the very edge of time. Astronomers are now hunting for the supernova of the first generation of stars, the colossal population 3 giants. Their explosive conclusions would have been events of almost incomprehensible power, likely far brighter than any supernova we see today. These were the universe's original heavy element factories, the first events to ever sprinkle metals like carbon and oxygen into the pristine cosmic gas. Observing one would be like finding a preserved trace of the very first life to walk the land, a direct glimpse into the epoch that first set the chemical evolution of the cosmos in motion. This search takes us to a period known as the Cosmic Dawn, the first few 100 million years after the Big Bang, when the first stars and galaxies flickered to life. It is a frontier of observation, a time so distant that its light has been stretched into the infrared part of the spectrum by the expansion of the universe. For decades, this era was shrouded in complete darkness to our telescopes. We had sophisticated theories about what must have happened, but no direct evidence. That is changing now with tools like the James Webb Space Telescope. Its immense mirror and sensitive infrared instruments are specifically designed to peer back into this formative twilight. Scientists are not just looking for the first stars themselves, which would be points of light, but for the brilliant, temporary flashes that marked their spectacular conclusions. They are scanning the deepest fields of the sky, searching for a signature that matches what our models predict, a supernova of unprecedented luminosity and perhaps unusual chemical fingerprints. Finding even one would be a transformative discovery. It would confirm our understanding of how those first stellar behemoths lived and reached their end. It would show us the exact moment the universe's chemical enrichment began, the initial seeding event for everything that followed. The light from such an event, having traveled for over 13 billion years, would carry the pristine signature of the first elements forged beyond hydrogen and helium. It would be a message from the dawn of creation, telling us how our long journey from simplicity to complexity truly started. The idea that we are stardust was not always scientific fact. It was once a daring piece of cosmic speculation. For much of human history, the elements were considered eternal and unchanging, simply the fundamental building blocks of a static universe. The profound truth that they are forged in stellar furnaces and scattered by stellar explosions represents one of the most beautiful syntheses of human thought. It is a story that connects the smallest scales of atomic nuclei to the grandest vistas of the cosmos, and its discovery required a collaboration of minds across disciplines. This grand unifying theory has a name, the B2FH Theory, drawn from the initials of the four scientists who brought it together in a landmark paper in 1957. Margaret and Geoffrey Burbidge, William Fowler, and Fred Hoyle. Their work was a masterful act of cosmic detective work, stitching together clues from three separate fields of science. From astronomy, they used the observed chemical compositions of stars and the energy output of the sun. From nuclear physics, they incorporated the rapidly growing understanding of how atomic nuclei could fuse and transform, knowledge being hard-won in laboratories here on Earth. From chemistry, they considered the very abundance of elements we find around us, the specific recipe of our planet and solar system. Before this synthesis, a dominant idea was that all the elements were primordial, created in some singular event at the beginning of time. But this presented puzzles. Why were some elements like gold or uranium so incredibly rare compared to common ones like iron or oxygen? The B2FH paper provided the elegant and dynamic answer. It laid out the specific nuclear processes that could occur inside stars, detailing how different elements were forged at different stages of a star's life, from the steady fusion in sun-like stars to the explosive nucleosynthesis of supernova. It proposed that the universe's chemical diversity was not a starting condition, but a consequence of stellar life cycles. Fred Hoyle, in particular, played a crucial role in championing the idea that the heavier elements must be created in supernova, a bold prediction that awaited confirmation for decades. The theory transformed our understanding from a static catalogue of elements to a living, breathing narrative of cosmic evolution. It proposed that the stars were not merely made of elements, they were the factories that produced them. This was the moment nuclear astrophysics was born, the fusion of the very small and the very large into a single, coherent story. The validation of this theory stands as one of the great triumphs of the scientific method. It was not proven overnight by a single experiment. Instead, its predictions were tested and confirmed piece by piece over the ensuing decades. As our telescopes grew more powerful, they found the chemical signatures in starlight that matched the theory's predictions. The detection of specific unstable elements in the aftermath of observed supernova provided direct evidence. The crowning achievement came much later, with the direct observation of a neutron star merger and its associated kilonova in 2017, which showed the rapid neutron capture process in action, creating heavy elements exactly as the framework had suggested. This journey from a brilliant theoretical insight to its observational confirmation illustrates a profound truth about our quest to understand the cosmos. It shows how human curiosity, by patiently connecting dots between the laboratory bench and the telescope's eyepiece, can unravel mysteries that span the entirety of existence. We did not just look up and see the answer written in the stars. We had to first imagine the possibility, then build the tools, and finally gather the evidence that we were, all along, the children of those very stars. This grand narrative of cosmic alchemy reveals a universe in a state of perpetual, creative transformation. From the silent simplicity that followed the Big Bang to the intricate chemical richness we see today, every step was driven by the magnificent and necessary cycles of stellar life and change. Stars are not merely points of light, they are the universe's primary artists and architects. They forge new atomic possibilities within their fiery hearts, and in their dramatic conclusions, they become the ultimate distributors, seeding the galaxy with the raw materials for everything that follows. Over billions of years, this continuous process of creation, dispersal, and recombination has woven the intricate tapestry of matter we are part of. You are a living testament to this epic story, a temporary assembly of atoms that have journeyed across the cosmos and through the hearts of ancient suns. The calcium in your bones, the iron in your blood, the oxygen in your lungs, each carries the history of a stellar event that occurred long before our world was born. This connection is not metaphorical, it is the fundamental truth of our physical existence. The next time you look up at the night sky, remember you are not a separate observer gazing at distant lights. You are looking at your distant origins, the very stellar furnaces whose lives and transformations built the world and everything in it. If this profound connection to the cosmos has amazed you, consider subscribing for more journeys into the heart of space's greatest mysteries. We would love to hear which element's origin story fascinated you the most, so share your thoughts in the comments.